The second major topic in our study of infinite series is Taylor series. In the first topic, we studied infinite geometric series. Then we expanded that idea to infinite power series. In this second topic, we'll focus on a Maclaurin series where the center of approximation is x equals 0. Then we'll expand that idea to a Taylor series where the center of approximation is x equals a, which includes the idea of x equals 0 as well. We'll make a difference between both of those series later, but first let's take a look at an exploration. This is in your booklet, and what I want to do is just set this up, give you a few minutes to work this out, and then come back and find out what the answers are. So let me explain the setup of this situation first. It says construct a polynomial with the following behavior at x equals 0. Here are all of the behaviors. That the polynomial's value at 0 is 5. The polynomial's derivative at 0 is x. So take the derivative, plug in 0, and you get 7. Second derivative at 0 is 11, and so forth until the fourth derivative. Now, we write these apostrophes until we get to the third derivative, and then in the fourth one we write a 4. It's called p super 4. Then the order is given here, which is basically the order of the derivative, the fourth order derivative. And then all of these columns here are basically showing us, or will show us, we're going to fill this in, what the actual terms of the polynomial are. The way you work this is you basically work column 1 and then column 2, row 2. Like so. So you're still kind of confused. Okay, what's going on? All right, this is what we do. This is eventually going to be our answer to this whole exploration, and you'll see why we do this in a moment. But when we look at this, the fact that p of 0 equals 5 right here, oops, that means the x to the 0 term is 5. The x to the 0 term is 5. Okay? So then that means if we take the derivative of that function as it is, it's basically p equals 5, then the rest of these below that are 0, all zeros, because we're taking the derivative down below. Now let's focus on C2, R2, column 2, row 2. If the derivative at x equals 0 is 7, then there's something right here in this original polynomial such that when you take the derivative of it, it's 7. All right, so let's do that. Well, that means that all of these are 0 as well. Now I want you to see the pattern, this 5 and 5 and 7 and 7 and 7 and so forth. Now, I'm going to set you loose in just a moment, but first I want to show you that to get this term right here, we're taking the antiderivative of this 7, which is 7x. So now what I want you to do is see if you could fill in all of these other boxes and eventually find the original function that would produce these values down below. And notice that the fourth derivative, so the fourth derivative of this polynomial up here, will give us 17 down here. So try that out, pause me, come back. Oh, and don't simplify your results when you put them up here. Just write them as products. Okay, I'm starting to fill these in for you. We're taking the antiderivative as we go up. And I have the final antiderivative as 17x to the 4th over 4 times 3 times 2. So notice how I didn't simplify these pieces up here because I want to show you exactly how we could generalize that process. Now, just notice that I gave you this problem, I gave you this situation that you don't really know much about. All you would know is that this polynomial here, that if you eventually take all these derivatives, you get these values down here. But let's answer the actual question. The polynomial that would satisfy all these results is that first line. And I'm writing that with all of the powers and the denominators as they are. I have 11x squared over 2 times 1, which is 2 factorial. And I have 13x cubed over 3 times 2, which is the same as 3 times 2 times 1, which is 3 factorial. And the final one is 17x to the 4th over 4 factorial. Now that stops there. It doesn't go on forever, but we could, if we really wanted to, we could write this as an infinite series. But here's the thing. I want you to see this so that we could do this next process here. That if we take the derivative and plug in 0, we get the coefficient of these x values right here. So what this is telling us is that these are the coefficients of all of the x values. And what happens with the powers and the denominators with factorial is they divide each other out. So let's apply that idea to this first example. And it's asking us to construct the 7th order polynomial and the Taylor series for sine x. So let's duplicate what's happening over here on this left column with sine x. So this will be the same setup that we do for both examples today, and as we continue, we'll plug in x equals 0, and if we do this in one straight line, it basically makes all of our work minimized. Sine of 0 is 0. Let's take the derivative, which is cosine x, and plug in 0. We get 1. And I'm going to do that for 3 more. And what we find is that this combo of 0, 1, 0, negative 1 will repeat itself, because if we take the derivative of sine 1, 2, 3, 4 times, we get back to sine, and that whole process repeats. So it's at this point that we start to repeat. All right, now what these are, these zeros, ones, zeros, and negative ones, those are coefficients. Those are the answers of this column of behavior, so they show up in the polynomial with the factorial. So let's write out what that polynomial would be, and I'm going to call that p sub 7, which is the polynomial of 7th order. And so the first term is 0. The next term is 1x to the 1 over 1 factorial, which I could just write as x. Now the next one, so that's that coefficient right there. The next one has a 0 coefficient, but I'm going to write it anyways. So it's 0x squared over 2 factorial. And then I'll use this negative 1. What I have right here are the first 4 terms of that 7th order polynomial based on these first 4 coefficients. Now I'll do 3 more. There we have it. 1, 2, 3, 4, 5, 6, 7, 8 terms. Oh, whoa, wait a second. I thought we were doing the 7th order polynomial. Well, let's go back. If we do the 4th order polynomial, that means there are 5 terms. But don't get confused by that. Don't try to remember, oh, I just do 1 more. Just remember the 4th order is the 4th degree. So going back to this situation here, we have the 7th order polynomial. It has x to the 7th. But this would be kind of a waste to write. We didn't really have to write all those terms. Let's simplify. Here we have our simplified form of the 7th order polynomial, and I'll explain what this means in a second, but I want you to notice that it's 1, negative 1, 1, negative 1, 1, negative 1, 1, negative 1, 1, 3, 5, 7. Hey, that's interesting. As we go on this journey through infinite series, we're noticing these patterns, and this pattern is that a Taylor series, a polynomial like this in green, that's representing sine around x equals 0, all of the terms have an odd degree, and sine is an odd function. Oh my gosh, that's so amazing. That means we're expecting cosine to have even powers. Now let's try to expand this into a general form. Let's start at n equals 0, and I'll explain a little bit more in a moment. But I need to raise negative 1 to the n. So if I raise negative 1 to the n, the first term, like the first coefficient I get is 0. So negative 1 to the 0 is 1. Now I need to raise x to a power, and I need to, if I'm using 0, that means the first power should be 1, but then I have to go up by 2's. So that means I'll multiply by 2 and add 1, 2n plus 1. And then my factorial is 2n plus 1 as well. Whoa, how did I know the 2n plus 1? All right, first of all, 2n would give me an even power. So 2n plus 1 would give me an odd power. But then notice that the sign, if we just use n, the sign of this one would be negative because it'd be negative 1 to the 1 to an odd power. All right, so this will be probably some of your most thoughtful pieces of working a question is like, what is the actual general term? So this is a general term inside here that has just x to some n value. And then where you start, you kind of have to think about, well, I'm going back to the first piece up here, and I noticed that my first term was 0. So that's a hint that you should start at n equals 0 if there is a first term that doesn't show up in your final result, basically this polynomial. All right, so that's the Taylor series. Well, what is a Taylor series? Let's talk about that. Here's the definition. A Taylor series is a sum, that's a series, is a sum of all the terms with the form that we just went through, starting with the exploration and as we did this example. F of 0, F prime of 0, F double prime of 0, F super n of 0, those all give us the coefficients. And then really there is a secret little divided by 1 factorial here. There's actually a divided by 0 factorial here, but 0 factorial is assumed to be 1, but it is kind of silly to write it there. And then the rest of this is just to explain why there are k's here instead of n's. If I were to write k here, then I could write n's here. But since I chose to put n's here, which is basically how many textbooks write it, then we'll use k's here. All right, so then that means that the sum could be written in this form. The other thing that I did just in that last example was I wrote out the actual polynomial. So the polynomial is called p sub n, or p sub n of x, and that's written in short as a Riemann sum, but as I wrote it out in the example, I wrote it out just as terms. So in this one, we don't go up to infinity, we go up to n, because we're choosing some 7th order or 4th order polynomial such that n is the order, and we'll write out those terms only. There you have it. That looks very similar to the actual general term of the series. In fact, that's what it is, because we're writing out the actual terms when we do the series, and we're writing out the actual terms when we do a polynomial. So I want you to notice the difference between a polynomial and a series. A polynomial is basically finite. Let me write that. This is a finite number of terms. And then this one, the series up here, is infinite. Okay. We're basically saying, hey, there is an infinite series that represents a function. Like if we add up all the terms, it's perfect. And that's what this is right here. This whole idea of an infinite series representing a function. But since we are like finite beings and we could only enter so many terms in like a calculator or on paper, we could just write the approximation as a finite sum of terms. All right, so that's the definition. Let's take a look at one more example just to get you used to the process. And we're going to do the same process that we did with sine here. And this one we're doing a 4th order polynomial, so it's not as long. And we're doing it for cosine 2x. So the chain rule shows up in here. And this is the last thing that I'll share with you. So I'm just going to set it up. And this one we have like a y notation, so we could say dy dx or d and then d2 dx squared, but just using prime notation is good. Y prime, y double prime, y triple prime, y super 4. So the 4th derivative, because it's the 4th order polynomial. The first derivative is negative 2 sine 2x. The second derivative is negative 4 cosine 2x. There we have all the derivatives, and we'll plug in x equals 0. Why? Because that's our center of approximation. And because it's at x equals 0, that's called a Maclaurin series. Here we go. Cosine of 0 is 1. And then the next term is 0 because sine of 0 is 0. This one we have cosine of 0, which is 1. Then we multiply by negative 4. We have 0 again. And then the last one, cosine of 0, is 1 times 16. What are all those? Oh my goodness, what are all those? These are all coefficients. We don't really have to take a formulaic approach to what we're doing here with a Taylor series, which, by the way, this is Maclaurin, because it's centered at 0, we just find out these derivatives and plug them into a polynomial. What does that look like? I won't write the 0 terms right now, I'll just write the actual ones. The first one is 1, x to the 0. It's the 0th derivative. And we have 4x squared over 2 factorial. How do we know it's 2 factorial? And then we have 16x to the 4th over 4 factorial. How do I know that? All right, two little patterns I want you to notice is that the 2 factorial matches the power of x. 2 factorial matches the power of x, which also matches the degree of the derivative, the order of the derivative. And then notice over here, x to the 4th, 4 factorial, which is the 4th derivative. Now I'll simplify, or I'll rewrite this so I can understand what's going on. I'm looking for a pattern here, and the pattern I notice is that 16 is also raised, is some number raised to the 4th power, and that happens to be 2. That means I could rewrite this in a general form. Now, you might be able to tell in the tone of my voice that I wanted to do one more thing, but actually that's it. We could write the general term for this and write it in Riemann sum notation, but we don't really need to do that because the question is asking for a polynomial, not some sort of general term. But I do want you to notice that the powers of these are even, yes, because cosine is even. So while the sine function would have these odd ones, 1, 3, 5, 7, the cosine function has the even ones. So what we're saying is that this 4th order polynomial, this, if you sketch this, that it looks like cosine 2x. Okay, thanks so much for learning with me. Until next time.